Welcome back, Quadrature fans. My name is Mary Milena. Today we're continuing geometry for quadrature, and we're going to look at affine type geometry or geometries. There's a whole class of them that I would consider as affine based. Strictly speaking, affine, at least this is well, it's a shared ignorance, but this is what I know of affine geometry. It's kind of strict parallelism this way and linear this way, okay? And to me, it seems like this is a natural for affine geometry. That's just the geometry of a Cavalieri shift, where you got strict parallelism this way, and then parallels this way, right? And, okay. So, we looked at this. We looked at curve. Last time we looked at y equals x plus x. And we asked the question, well, what does that look like? The plot of this. And you could say, well, it's y equals 2x. You plug it into your computer and you will see a plot something like this, 0 to a, 0 to 2a. So it's a 2 to 1 slope. You can see that the slope is 2 here. But I would venture to say that the plot of x plus x is a plot of x plus another plot of x. So you got two functions. This is the kind of shape you get when you plot x plus x. And that does not look like this, okay? At least, we're trying to get this from here to here. And our Euclidean geometry insists on a right angle right there. And it's not willing to budge. And so we're kind of in a pickle. So we need some kind of a different geometry. I like to do what I'm able to do in algebra. I'd like to do in geometry. Can that be done? Is there such a geometry? I think there is, at least what I've seen and read and looked at the internet. This affine seems to be like a good candidate because it allows me to do this downshift. And then I can stack. For example, you take this, you shift it down. Now it matches here. Now that looks like this. Now you can add them together. And the big question, of course, was, well, okay, look at the area. Area under a Cavalieri shift is invariant, doesn't change. Okay, I kind of see that. That seems to be an easy notion to understand. If you understand sliced bread, sliced cheese, and a deck of cards, I think you'll understand that. But the notion of slope is a little bit challenging because, you look at this thing and in this affine world, you would say that this slope, well, it's not the same as this slope here, and yet they're the same functions. But in affine geometry, what's the definition of affine geometry? Oh, where's my computer? I used to have it here. Oh, well. It's the notion where geometry, but without the metric notions of distance and angle. That's what I found on Wikipedia. So you take Euclidean geometry and forget the notion of some kind of an absolute metric. Like here's a meter stick that's tied to some standard in Sèvres, France, right, where they have the official length of the meter. Well, that's an example of a metric system, right? This is says there's 10 centimeters, right? And that's throughout the whole world, and it's this way or this way. Well, in affine, affine is a little bit weird. In affine geometry, basically, let's look at this. Here's our Euclidean, and let's say that we agree, you know, this is A, here's A over 2, here's B over 2. Okay, so that's our distance. Euclid tells me from here to here is A, from here to here is B. And Euclid has this nice ruler. He's got a protractor. He can measure distances, even distances between here and here, which is total nonsense in affine, I think. But to affine, he says, okay, Euclid calibrated me. Euclid told me I'm 0 and I'm A, and here's A over 2. And so he's happy. But now affine goes along and he gets shifted. And here he gets shifted even more, but he's saying, oh, I'm still A. 0 to A, because that's what Euclid told me. He told me to write down these, put down 0, put down A, that's your distance, so I'm keeping that. But clearly it's different, because, you take a protractor from here, and here, this is longer, right? But affine doesn't have a protractor. We come with a built-in protractor. I'm holding it in my hands. So, there's your... But affine doesn't have that concept, so no protractor, and he doesn't know anything about angles either, so yeah, it's already kind of weird, but to him, this diagonal slope, well, that's rise over run, that's B over A to affine. To Euclid, it's B over A, we agree. Now you've shifted it. Oh, well, Euclid says, it's B over 2 over A. Oh, that's 1/2 of this. Affine says, I don't know anything about distance. I mean, if you say so, but I'm still A over here. My run is A. My rise is B, so I'm B over A. And so it is. And you can shift it any way you want to. Here's your diagonal. Keep shifting. Here, Euclid says, your slope is 0. You're flat. Affine says, I'm rise B over A. B over A. No matter what you do to me, I can't tell. I have no metric notion of distance or angle. I cannot distinguish this from this, from this, from this. They're all the same to me. That's affine, okay? And so, okay, we use this notion and we come to, I equals x plus x. And here we can see that for every run of 1, we get a rise of 1. So this one contributes a slope of 1. This one contributes a slope of 1. For a total of a slope of 2, right? 2. Okay, you kind of get that. But, I'm trying to get, this is really the geometry of this Cavalieri shift. What's happening? Well, in order to go from here to here, we need a Cavalieri shift. And in a Cavalieri shift, well, the area is the same. This area is the same as this area. Hasn't changed. Okay, area is kind of easier, at least in my mind, to understand, but look at the notion of slope. Slope to affine, well, it's rise, which is A over A, this distance, A is the same distance as this distance. He can't tell. It's just the way it is. That's the way affine is. So you look at this scenario. He can't distinguish this either. You know, to him, you can move this point to here, which is what you get over here, or you can go all the way up to here. They're all the same. And each of them contributes the same way with area and with slope. But now we run into a interesting problem with, well, what if we want a little bit different thing? Let's say we want, ooh, we don't want it to fall down, do we? Stay up there, baby. Y equals x squared plus x. What does this look like? Well, this looks rather interesting. Okay, let's plot it over the interval from 0 to 1. Let's see, we always use simple diagrams. Okay, so we're going to do this and this, right? That's what that looks like, right? Y equals x squared plus x. That's one way to look at it. Another way to look at it is, well, we can do the same thing, but we can put the x squared on top, and we can put the x over here. This is an alternative view, right? There's nothing wrong with that. They're both okay. Okay. And so now if we do a affine Cavalieri shift, just a straight shift with this one, what happens? We're going to do a shift down. So let's draw that. All right. So we gotta go from here down to here. Right, this box is now going to shift down. We're going to keep this original here. It's going to look like this. See our box? Now it shifted from here to here. And what happened to this? I gotta look at that, okay. There, so we have this, and we have this. Right, we did a Cavalieri shift, we did an affine operation, strictly parallel, down this way and this way. And unfortunately that doesn't work too well because this is not the shape that I'm after. There's this hole over here. That's not what I wanted. Of course, if we just rearrange this and put this on the bottom, yeah, with this one we do, right? So here we have our original, and then here's our new box. And this one works good. You see that? We've taken this and we've downshifted it using Cavalieri's shift. And this one fits nice. No holes over here. But already you can see, you know, one has a hole, the other doesn't. This is kind of problematic. I mean, this works okay for linear, because it stacks well, but it doesn't work well for curves. We need a little bit of a twist. We need a what I call a curved affine. I don't know if that even makes sense, but there's parallelism. See that parallelism? It's curved. And here's what a diagonal looks like. See this diagonal? If you were to plot it in this twisted, warped geometry, curved affine, well, it would look to us, it would look like a curve. But to this curved affine, or Cavalieri affine, we need a term for it. I don't know how to call it, but we got to distinguish from the linear type affine, or just affine. It looks like a curve. But to the affine, it's as straight as an arrow. The slope is constant. Because for every run, for every a over 2, he's registering, well, b over 2. And so then you go another a over 2, and then you get another b over 2. So it's constant. The slope to affine equals b over a. And here, but what about the slope to Euclid? Well, that equals question mark because it's changing all over. So you talk about weird geometries. Yeah, it's weird to us or to Euclid, and we kind of live in this world, and we like our right angles, and everything is nice and straight. But why do we need this kind of a geometry? Well, it's precisely this is the problem that I'm trying to address. A straight affine, it doesn't cut it. I'm stuck with this hole, and I'm trying to make it like this. And what are we going to do? Well, look, imagine this. So, yeah, we've got this, but imagine some kind of a curved affine. See this? Let's say I slice this up, this thing, slice them up, just like cheese, or just like deck of cards. Imagine that this was on a deck of cards. This is all on my deck of cards. And initially we're starting out linear. And we have a problem here. We want to fill this gap. We don't want any gap. So we push down, and we basically make it curved affine. You see this? And now our deck of cards will fit. You see this? It's the scenario, it's the same thing as this. It's this notion of curved parallelism. These are still parallels, right? The box is still there. This is a box, but it's curved. And again, it's the geometry of the Cavalieri shift. That's how I understand it. Now, what does it do to distance? Oh boy, distance has really been warped in this system because, oh wow, at least in a straight affine, you have essentially a rubber band and everything stretches equally. If you have 0 on a over 2, and you stretch it, well, everything stretches equally. You could think of rubber band geometry as an affine thing. Why not? But what about in curved affine? It gets weird. And, this was with a supposedly honest rubber band that stretches equally. Well, if we make a dishonest rubber band, I don't know if you can see this. Can you see this? Do I need to come closer? Is it even legible?
A little bit.
Yeah.
Over there it was. I could just zoom into it.
Zoom in over here. Okay. See it?
Yeah.
There. You can see that the thinner portion now stretches more than the fatter portion. That, this notion of equal spacings, that's no longer there, and that's kind of what happens with the distance in a curved environment. Let's say that we have just a rectangle, 0 to A, and we try to fit it onto some kind of a shape which goes down, wee, 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 like this. Something like this. 0, A, right? Well, you can see that the distance, he's still going to call it 0 to A, but he's going to try to fit in here. And so all of this distance to him, to this curved affine, well, here's A over 2. And so to him, that's A over 2. Okay, so from here to here is A over 2. And then from here to here is another A over 2. And you can kind of see that this is crazy. This is not even constant. Everything's weird here. Wow. I'm kind of struggling with this too. Maybe I got it wrong. Maybe I'm crazy or something. That's what happens when you're in a COVID lockdown. You start thinking crazy math. Okay, but anyways, B, whatever it may be, we're dealing here with a Cavalieri type geometry, and we're trying to get to this shape, and we're starting out with these shapes originally. And how do you go from here to here? Well, you need a Cavalieri type operation, Cavalieri geometry, Cavalieri affine shift. That's my thinking. So, anyways, think about these things, chew on them, and remember, things get even crazier. We talk about parallelism, and then you got curved parallelism, and then we talked about Salvador Dali, which, well, here's what Salvador Dali type system would look, right? Let's say you've got curved, 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 but now, instead of straight, now curve it. Now imagine this. So what does a diagonal look like? Look at this. See that? This is Salvador Dali type geometry, affine. And here, it's 0 to A, 0, well, let's say B. So what's the slope of this line? Well, he says M affine equals B over A, because that's what he is. For every little bit of, B over 2 rise, I get A over 2, right? A over 2, B over 2, and it's the same story wherever you are. He's as straight as an arrow. Does he look like he's straight as an arrow? Yeah, you better believe it. Salvador Dali tells us that he's as straight as an arrow. So let's see what Salvador Dali looks like. Yep. Straight as an arrow. You better believe it. Anyway, so before there was quadrature, no, before there was calculus, there was quadrature.